The universe tells a story that moves in only one direction, forward. We remember the past, live in the present, and march toward an unknown future. This forward flow of time feels absolute. But is it? The dream of time travel fascinates us, but it's tangled in paradoxes. Imagine going back to prevent your grandparents from meeting. If you succeed, you're never born. So, who went back? This is the grandfather paradox, a logical knot that makes time travel seem impossible. The one-way street of time is governed by the second law of thermodynamics, entropy. Entropy means things move from order to disorder, like an ice cube melting or an egg shattering. You never see the pieces reassemble themselves. Time, like heat, flows from order to chaos. Our bodies, too, are subject to entropy. Aging is entropy's slow victory over our biology. This relentless march toward disorder gives time its direction. Reversing time would mean reversing entropy, unscrambling the egg, defying the universe's rules. The real challenge of time travel isn't building a machine, it's fighting the universe's fundamental tendency toward chaos. The flow of time, driven by entropy, is a current too strong to swim against. Or is it? Maybe our understanding of time is incomplete. Perhaps there are hidden currents in the river of time we haven't discovered. The journey to find out begins with the revolutionary ideas of a man who reshaped our understanding of space and time forever. The arrow of time may seem unbreakable, but physics is full of surprises. Let's see where the story leads. For centuries, time was seen as a universal clock, absolute and unchanging. Then Einstein shattered that idea, revealing space and time as a single, flexible fabric spacetime. Massive objects bend this fabric, creating gravity. Not as a force, but as the shape of space-time itself. Imagine a cosmic trampoline. A planet creates a dip, and objects follow the curve. But Einstein's insight went further. Gravity also warps time. The stronger the gravity, the slower time flows. This isn't science fiction, it's measured reality. GPS satellites tick faster than clocks on Earth because they're farther from gravity's grip. Even your head ages slightly faster than your feet. Near a black hole, time slows dramatically. An hour near the event horizon could equal years far away. The movie Interstellar visualized this, but it's rooted in real physics. Time is not universal, it's relative, and gravity is its master. The rigid universal clock is an illusion. Our experience of time depends on where and how we exist in the universe. Einstein's revolution opened the door to new possibilities. Could time be bent so far it loops back on itself? If gravity can stretch and slow time, could it bend it into a loop? Einstein's equations allow for closed, timelike curves, paths that return to their own past. Imagine a hallway where you walk forward and emerge at an earlier moment. Theoretically, wormholes, tunnels through space-time, could connect distant points, even different times. Accelerate one end of a wormhole near light speed, and time at each end falls out of sync. Step in one end, emerge in the past at the other. But creating and stabilizing a wormhole would require exotic matter with negative energy, something never observed. Other ideas like spinning cylinders are even more fantastical. The universe's math allows time loops, but reality makes them nearly impossible to build. Still, the possibility challenges our understanding of cause and effect. Suppose we build a path to the past. Now we face the real problem, paradoxes. The grandfather paradox: change the past, erase your own existence. So, who changed it? The bootstrap paradox: give Shakespeare his own plays. Who wrote them? These loops break the chain of cause and effect. In our world, causes precede effects. In a time loop, effects can become causes, or events can happen without origin. This logical chaos is deeply unsettling to physicists. The universe is governed by consistent laws. Paradoxes threaten that order. Maybe time travel is forbidden to protect reality's logic. Entropy poses another barrier. The past is more ordered than the present. Traveling back would mean reversing entropy, violating the second law of thermodynamics. It's like trying to unbreak the egg. Both logic and physics seem to guard the past from interference. But is there a loophole? For decades, paradoxes seem to rule out time travel. But quantum mechanics offers a new perspective. Physicist Lorenzo Gavasino suggests the universe might self-correct, using quantum randomness to avoid paradoxes. At the quantum level, reality is unpredictable. Particles flicker in and out of existence. Imagine you try to create a paradox. A random quantum fluctuation jams your gun, or a gust of wind diverts your aim. The universe doesn't need to intervene consciously. Randomness nudges events onto a consistent path. The same goes for the bootstrap paradox. Your manuscript burns, or you forget your mission. Quantum fuzziness ensures contradictions are avoided, not solved. The universe edits out paradoxes through chance. Instead of breaking, reality gently steers itself away from logical disaster. The past remains safe, not by force but by probability. This self-correcting universe is an alternative to the many worlds theory, which multiplies realities to avoid paradoxes. Gavesino's work suggests we don't need infinite universes, just one, with built-in consistency. Quantum fluctuations enforce the rule. You can visit the past, but you can't change it. You are always part of history's script. Any attempt to create a paradox is thwarted by probability. The gun jams, the book burns, the butterfly escapes. The universe keeps its story coherent, not fragile but robust. Free will may be limited in a time loop. Physics ensures consistency. The past is resilient, protected by quantum reality. You can't break history, you can only play your part. The universe doesn't need parallel worlds to protect itself, it's self-sufficient. Building a time machine remains science fiction. The energy and technology required are beyond our reach. Even Stephen Hawking joked about this by throwing a party for time travelers. No one came. Experiments have only managed to rewind a single electron for a split second. Reversing the entropy of a human is unimaginably complex. So why study time travel? Because it probes the deepest laws of nature. Time loops appear where our best theories, relativity and quantum mechanics, collide. Studying them teaches us about the structure of space-time and the rules that keep the universe logical. Even if time travel is impossible, the quest reveals the profound order of reality. The paradoxes of time travel may be the universe's way of protecting itself, and understanding them is a journey worth taking.